Imagine catching a planet in the very act of being born. This is a groundbreaking moment in astronomy. Recently, scientists managed to capture an image of a newborn gas giant planet named WISPIT 2b, nestled within a broad gap of dust and gas circling a young star similar to our own Sun. This remarkable observation was made possible thanks to the European Southern Observatory's Very Large Telescope, ESO VLT. This newly formed planet appears as a compact, distinct point sitting quietly in the dark spacing between luminous rings of material orbiting the star. Observations over time reveal its position changes consistently with an orbital path, confirming it orbits its host. The star, named WISPIT 2, is incredibly young, only about 5 million years old, which essentially provides a real-time snapshot of a star system still in the process of assembling itself. Leading this exciting discovery was Rochelle van Capelleveen from Leiden University.
Her team brought together specialists from various institutions, combining their skills and knowledge to firmly verify the planet's existence. Why is this significant? With almost 6,000 confirmed planets orbiting stars beyond our Sun catalogued by NASA's Exoplanet Archive, most are detected indirectly through effects like gravitational tugs or dimming starlight during transits. Directly observing a planet caught in the midst of formation is exceptionally rare. It offers a unique window for scientists to test and refine their theories about how massive gas giants grow and how their gravity carves the intricate rings and gaps observed around their stars. Seeing both the infant planet and its surrounding disk simultaneously allows researchers to directly connect the disk's structure with the planet's influence. This linkage is fundamental to understanding why planetary systems end up so diverse in their layouts. The ESO's Very Large Telescope, equipped with the sphere camera, was crucial in isolating the faint glow around the star. It unveiled a gorgeous, multi-ring disk extending to about 35 billion miles, 56 billion kilometers from the star, a scale roughly equivalent to the edge of our solar system's Kuiper belt. Within this expansive disk, several gaps separate the bright rings, and it's one of these gaps that hosts the compact light source now identified as the infant planet. By monitoring the system across multiple nights and months, astronomers noticed the point source shifting position in a pattern that perfectly matches Keplerian motion, basically the way planets and objects orbit in a stable, gravity-bound path. Importantly, the planet remains closely linked to the star against the backdrop of the cosmos, confirming it's not just a distant, unrelated object drifting through space. In near-infrared imaging, this young world glows due to leftover heat from its recent formation, making it distinguishable from the fainter, polarized light reflected by tiny dust particles in the disk. But here's where it gets even more fascinating and a bit controversial. Another group reported a strong H-alpha emission signal from the planet. H-alpha is a specific deep red glow produced when excited hydrogen atoms lose energy. Captured using the MAG-AO-X instrument in Chile, this emission is a telltale sign of active gas accretion, which means the planet is still gathering and building its atmosphere from surrounding material. This visible light signature, when combined with the infrared data, conclusively identifies the object as a newborn giant planet still growing. This dual evidence, both thermal glow and gas accretion, provides a robust and consistent picture of a giant planet in its early formative stages. It also opens multiple avenues for tracking how its brightness and environment might change in the coming years. Interestingly, WISPIT 2b represents the first clear detection of a planet embedded within a multi-ring disk, offering an unprecedented natural laboratory. The planet's gravity likely plays a key role in maintaining the observed gap by interacting with the material there, redistributing angular momentum and effectively sculpting its surroundings. The immense outer disk stretches to nearly 35 billion miles, while the planet orbits closer at about 5.3 billion miles, or roughly 57 astronomical units, from its star. Because the disk is exceptionally bright and sharply imaged, scientists can measure detailed properties such as ring positions, the widths of the gaps, and even the vertical height of the dust surface scattering light. These measurements help estimate disk viscosity, a crucial factor that influences how quickly the disk evolves and how planets migrate inward or outward. For context, astronomers often use the astronomical unit, AU, to describe distances within planetary systems, where 1 AU is the distance from Earth to the Sun, about 93 million miles, 150 million kilometers. This approach keeps the scale relatable and avoids confusing jargon for newcomers. WISPIT 2b's discovery follows a milestone first made in 2018, when the planet PDS-70b was identified forming inside a large cavity in its disk. That system famously revealed a second forming planet later, making it a cornerstone in understanding planet formation. Now, WISPIT 2b introduces a different but equally valuable case, a young sun-like star with a well-defined ringed outer disk and a forming giant planet located farther out. This second example is vital for testing and improving models about how giant planets emerge and how their nascent environments develop. Van Kapelveen reflected on the finding, saying, "Discovering this planet was an amazing experience." She emphasized that the clarity and simplicity of this system make it a perfect benchmark for future studies, allowing different research teams to compare their models against the same set of detailed observations. Looking ahead, follow-up studies with advanced facilities like ALMA, Atacama Large Millimeter Submillimeter Array, can map the movement of gas near the gap, searching for subtle disturbances caused by the planet's gravitational pull. Moreover, the James Webb Space Telescope, JWST, can perform spectroscopy to analyze the planet's emitted thermal radiation in detail and detect molecules within its young atmosphere. Further precise measurements of the planet's position over time will refine its orbit and eventually provide a dynamical estimate of its mass. Comparing this mass with the width of the observed gap will offer a critical test of existing theories that link a planet's gravity to the disk structures it creates. The combined results, rigorously reported in the astrophysical journal Letters, offer a compelling narrative of a giant planet caught in its cosmic nursery. But here's the big question to ponder. Do these types of observations challenge our current understanding of planet formation? And can the models developed around systems like PDS-70 and WISPIT 2 fully explain the diversity of planetary systems observed across the galaxy? What do you think? Does WISPIT 2b represent a universal blueprint for planet formation? Or are such cases unique cosmic coincidences? Share your thoughts and join the conversation. Image credit, C. Ginsky, R. Van Kapelveen et al.